Yeah, so I titled my talk Experiments in the Energetics of Quantum Measurements. So it's been really amazing to be part of this collaboration and also be at this workshop and this community of quantum thermodynamics for the last almost 5 years or so, and to try to do experiments that help us get at and talk about interesting questions in quantum energetics. So if kind of reflecting on my evolution of my understanding of this field, some of the questions that were floating around back at the KITP conference, whenever that was, 2019, maybe? 18. It was 18, well, time flies, 5 years ago. You can kind of boil down some of the key questions into 3 simple examples we can make with the qubit. So the first example is if I have a qubit in its ground state, qubit Hamiltonian, and I apply a pi/2 pulse to this qubit to put it in a superposition of its ground and excited states. And then I make a measurement. One of those measurement outcomes means the qubit's in a higher energy state, and the lower other energy outcome, measurement outcome, means the qubit's in the lower energy state. And so one could ask, where does that energy come from? If it's in a higher energy state, maybe we'll make it a poll. So, Alexia, where does the energy come from? From the pulse. So you can say, oh, this looks really interesting. That the measurement is making a qubit energy. Well, where does the energy come from? It comes from the pulse. It comes from the preparation here, the work done on the qubit by that preparation pulse. So not super exotic yet. Okay, so the second example is qubits in a thermal state. So inverse temperature beta. And we make a measurement of the qubit. And again, we could have the qubit be in a high energy state, low energy state. You say, where does the energy come from? In this case, if we find the qubit in a high energy state. It was already, I would say that it comes from the reservoir, that there's some, that it comes from the thermal environment. Fluctuations. And I think maybe part of that is we spent a lot of time doing sort of experiments where we demonstrate Jarzynski's equality, and that in this sort of situation, even when we have drives on the qubit and so forth, energy in the end that is revealed when you have it in high energy state comes from that thermal reservoir.
Is there a drive in this one?
There's not a drive in this one here, but you know, we did experiments where we drive the qubit and it's evolving while we're making continuous measurements. And you know, for me, it wasn't clear where that energy is coming from, and maybe it's still not very clear, but my colleagues say no, it comes from the reservoir, the thermal reservoir.
But nothing happens when you measure.
Nothing happens when you measure. So you can say it's already in the excited state. I like that too. That it was in a mixture of these 2 states.
And like the former case where something happened.
Good. Okay. So even better. It was already in the excited state. It was there because it occupies that state with the thermal probability given by the Boltzmann factor. Excellent. Okay. So the final example, and maybe the most interesting one, is let's say the qubit is again its ground state, but we now measure it in the X spaces here. So I can start to use my laser pointer. Okay. Well, in this case, we have 2 measurement outcomes, the plus X and the minus X eigenstate. And in both of these cases, the qubit's in a higher energy state. So this is quite interesting. And where does the energy come from? Lexi again, I think she would say comes from what we call quantum.
Now you can pick it
up. Energy here comes from what we call quantum heat. And I think back in 2018, this was felt like a controversial idea. There was a lot of discussion about how do you talk about these things. And that's why it's an interesting question. And this happens because the measurement doesn't commute with the system Hamiltonian. So it has to do with incompatible observables. And I would say that incompatibility of different observables, different operators, is the core aspect that makes quantum mechanics interesting and makes quantum mechanics powerful. So, of course, it's the basis of wave-particle duality, that there's a commutation relationship between phase and number. So anything that has to do with wave-particle duality comes down to non-commute observables. It's the basis of uncertainty relations. Also, this measurement disturbance relation, which is tells us about how the sort of precision of some measurement and the disturbance on another one are bounded by the commutation of 2 observables. I think this is the same relation as the Ozawa bound I presented yesterday, so the exact same thing. It has to do with quantum measurement limits, so the Stater quantum limit and the Heisenberg limit. I would argue, and I haven't figured out how to articulate this quite, but I think it's actually the basis of the power of quantum algorithms, that Shor's, let's see, Shor's algorithm has to do with its quantum point phase form, has to do with interference, wave nature of states. But in order to read out the result, you need to make measurements, local measurements that are sort of harness the particle-like nature. So I think that that's also possibly the power behind quantum mechanics.
Yeah, just quick question. By precision of measurement, you mean the value by vibration?
Yeah, so the signal to noise increases like square root of n. So oh, this one here. So this is like the precision of the observable A, and eta is sort of the disturbance on observable B. And so I think if we took this term here and put it in the denominator, it would look like that is upper bound. Okay, it's also the key aspect of this sort of local versus global observables that Andrew talked about in his talk, and then Ronnie mentioned in his talk that the commutation between your control and your Hamiltonian tells you about the types of whether or not systems fully controllable or what you can do. So again, everything comes down to incompatible observables. And so I would say that the energetics associated with incompatible observables will get to sort of the core questions of quantum thermodynamics and quantum energetics. So that's why this should be interesting to study. So let's go back to this example where I have the qubit in the ground state and I make a measurement in an operator doesn't commute with the qubit Hamiltonian, and the system ends up in higher energy states in both cases because how is energy conserved? So the energy has to come somehow from what we're doing to measure the thing. So it comes from whatever goes into this MX measurement operator. And so in the case we'll be probing with light, we'll find out that this energy conservation comes from a frequency shift on that probe, like the passive part of the qubit. So how do we do experiment to see this sort of effect, or to study conservation of energy in this measurement context? The first thing we'll do is change the basis that we're working at. So here I'll make the Hamiltonian of the qubit be along sigma x, so some Hamiltonian omega sigma x, and I'll make measurements in the z basis because that's what's easy for us to do in lab. As Alexia noted yesterday, when you're talking up there, it gets quite warm. It's like a little like that. So, okay, so that's the plan, and then okay, so then when we make a measurement in the z-axis, we'll project it to the ground or excited state, but those will both be higher energies states in the qubit basis. And so equivalently, or how we do this experimentally, is we're actually going to drive the qubit resonantly with the resonant drive, so that in the rotating frame, we're able to produce this Hamiltonian. And we'll make these Z measurements with this dispersive interaction with the microcavity, given by interaction Hamiltonian. That's chi, the dispersive interaction rate, times the photon number operator in the cavity, times the qubit Z operator. Okay. And along the way, we'll see some of the kind of classic effects in quantum measurement and quantum optics. That is the quantum Zeno effect and the Mollow effect. I'll explain this as we go. So, okay, so here's the experiment. And we have a trans-Mon circuit. Just think of it as a two-level quantum system for the purposes of this talk that's embedded in the three-dimensional microwave cavity. And we can send microwave signals into the cavity and they come out of the cavity. And the interaction between the qubit and the cavity is given by, again, this dispersive interaction. And there's dissipation in the system. Cavity dissipates at a rate kappa, and the qubit has some dephasing that may be given at a rate gamma. Neither of those become particularly relevant in this talk. We've set this up so that the input signal is very weakly coupled into the cavity. So in fact, the vast majority of the photons are just reflected off the cavity, not carrying away any information about the state of the qubit. There's no phase shift in the input port. And so only a very small fraction of the photons make it into the cavity, maybe 1 in 1,000 or 1 in a million of those photons. And those photons then leave the cavity via the output port with very high probability. So in the context of the waveguide talks yesterday, we've got an even simpler waveguide where we sort of sneak the photons into the waveguide and then just come out. So it's a kind of even simpler situation. Okay, so we're operating in the strong dispersive regime of circuit quantum electrodynamics, which is where this dispersive interaction is greater than the dissipation rates. And the way to see what that means is that I look at the cavity transmission as a function of frequency. I'll find that the sum of the interaction is that the cavity frequency depends on the state of the qubit. So the cavity transmission frequency is one frequency of the qubits in the ground state, different frequency of the qubits in the excited state, and those two peaks are well separated compared to the dissipation rate of the cavity, which is like kappa. Now, this realizes the ideal measurement limit that Nicolo was talking about in his talk yesterday, where we have a pi phase shift depending on compared to the different qubit states. That is, if I look at the phase as a function of a frequency, here we have a phase shift across pi across the resonance to the ground state. Here we have a phase shift of pi for the resonance across the excited state. So the phase shift here is pi, or approaching pi. That's the ideal limit. Okay, so now the signals that are output from the cavity are routed to some sort of detector. And this detector is a Josephson parametric amplifier operating in phase preserving mode. We'll talk more about that on the next slide. But the important part is that the signal that we detect is demodulated into two quadratures, I and Q in phase, quadrature phase of the electromagnetic field. And the idea is that these are ultimately proportional to the annihilation and creation operators for the photons in this transmission line, which are then also proportional to the annihilation and creation operators for the photons in the cavity. So we're able to track, something that's proportional to the photon creation annihilation operators in the cavity. Okay, and then we're going to probe the system right at the frequency between these two ground state resonance and excited state resonance for the cavity. So now let's look at what that emitted light looks like. And so we'll just sort of calibrate the background. What does it look like if we don't probe the system at all? If we drive the cavity with no photons, we're just looking at the vacuum fluctuations of the cavity. But we're going to drive the qubit to create this Hamiltonian in the rotating frame, omega sigma x. Okay, so we're going to calibrate the background of the system, and so we acquire the demodulated signals I and Q, and so that's some complex signal which we record for some period of time, and then we take the Fourier transform power spectrum of that signal. Okay, and so what we see schematically here is that there's a sort of a broad frequency dependent background to the signal shown here that changes as we look at the frequency of the Fourier transform. And so even when we're not probing the signal. So what's going on here is we have your quantum fluctuations in the mode that's amplified by the parametric amplifier. And the parametric amplifier may also have its own quantum fluctuations associated with it. We call it T parametric amplifier. And so the sum of these two are amplified by the parametric amplifier's gain, and then added to the noise of the following Hemp amplifier. And that leads to the overall noise power that we detect. The paramp has a certain gain that has a certain shape. It's the same sort of shape here. And so when in fact, when I turn off the Hemp amplifier, I see this level of gain here, or this level of noise. And so the conclusion of this slide is that, when I amplify the system, what I see here in my signal, my background, is all just the amplified quantum noise associated with my detection scheme. So I'm able to resolve really the quantum fluctuations of this signal above the background noise floor of all my classical detection apparatus. Yeah, question.
What's omega p?
Omega p is the probe frequency that I'm using to drive the thing. So because it's the same thing as omega c. So I'm probing right at that specific frequency, and so that's the Fourier transform relative to that frequency.
What is a Hemp?
So what does the Hemp do? The Hemp amplifier is just an amplifier that makes the signal bigger. The idea is that the classical electronics here have a noise level with them that's associated with a temperature that's something on the order of 10 to the 5 Kelvin. Very noisy electronics. Here, the noise temperature associated with quantum fluctuations, h bar omega q over 2 kb, is something like 100 millikelvin. And so I need to take this noise of my quantum fluctuations and make that large enough that it overwhelms the classical fluctuations associated with my room temperature electronics. And so that requires, not just one Hemp amplifier, but several amplifiers. But the key piece is that this parametric amplifier adds the minimum amount of noise to the system mandated by quantum mechanics. And so when I see the noise in my systems dramatically increase with the parametric amplifier, that convinces me that the fluctuations of this background that I see is really due to this quantum noise in the system. So we're mostly detecting the quantum noise associated with this parametric amplifier and the vacuum fluctuations of this electromagnetic mode that couples to our cavity.
What does TH also in the dilution refrigerate?
So that's the noise temperature of the Hemp amplifier.
Yeah.
And that's something like 10 Kelvin.
Is the parametric amplifier a Josephson amplifier or?
Yes, it's Josephson parametric amplifier.
Okay.
So nonlinear circuit that we drive at certain frequency. Let's see. I know when you ask what omega p is, actually lied to you. So I'm thinking about it more carefully. This is omega c. We probe it at cavity frequency there. Omega p is actually the pump frequency of the parametric amplifier. And we pump the parametric amplifier at a frequency that's different than the frequency that we're interested in analyzing. That puts us in this regime of phase preserving amplification. And so let's see. I'll draw it here in a next slide. We're just going to set the cavity frequency to this frequency here. And so the pump frequency is here. And so we're going to drive at this thing here, some detuning away from this where the gain is relatively flat. These things. Now, what does it look like when we make a measurement of the signal? So still somewhat schematic. If I prepare the qubit in the minus x state, so now it's in one of the eigenstates of this Hamiltonian that we're creating with this drive on the qubit, and now I probe the cavity for 2 microseconds. I'll take the Fourier transform of the demodulated signal. What I see is a little peak here at some frequency on top of this broad background. Show you the actual data eventually. And if I prepare the other eigenstate of the qubit's Hamiltonian, then I see another peak riding on this background. That's a different frequency. Okay, and so I'm interested in these signals, and this is roughly what we expect, that there's some sort of frequency shift of the probe. That is, we sent it in at this frequency here, and it's coming out at different frequencies depending on the state of the qubit. Okay, so what I'll show you in the coming forthcoming slides are the background subtracted power spectrum of the system. So we can take the power spectrum of the signal with the probe on, and we can subtract the power spectrum when the average power spectrum when the probe is off. And because the signal and the power spectrum uncorrelated, this just gives us back the power spectrum of our signal with the background. So here's an example of the type of experimental data that we cover. There's a lot of things going on in the slide, so let me walk through it. The key point is that, as I indicated on the previous slide, if I prepare the qubit in one of the eigenstates, say plus, I see a peak at a frequency here. And if I prepare the qubit in a different eigenstate, I see a peak happening at frequency here. Now, there's a lot of different frequencies at play here. So there's the probe frequency. So I think my notation is a little bit wacky, so I apologize for that. This is the frequency here that we're probing the system, we're driving the qubit at. So essentially I called omega C on the previous slide, I apologize. And then there's that omega C plus or minus the energy of the qubit, so shifted by this Rabi frequency, and those are these frequencies here. And then there's also the cavity frequency, or the shifted by the qubit state. So this is the omega cavity when the qubit's in the ground, say the ground state and excited state. And so those are indicated here. And so what we're seeing is actually just a frequency shift in the emitted spectrum that corresponds to the qubit energy omega. Okay. So here's that spectrum again. Now, as I change the Rabi frequency of the qubit energy level, and so given that we're applying a pulse of a fixed bandwidth, fixed duration, equivalently, I'm changing the bandwidth of the pulse relative to the qubit energy. So this is again can be compared with Nicolo's talk yesterday, which I have to guide you through about the tuition. So here I'm increasing the Rabi frequency in this direction here. And if I prepare the qubit in different eigenstates, I see a frequency shift. So in one case, I see a frequency shift that the emitted spectrum is shifted to lower frequencies. In another case, I see that the spectrum is shifted to higher frequencies. And this is what we expect, that for one of the qubit states, we prepare this ground state as Hamiltonian, we make a measurement on the Z basis, the energy increases. Where does the energy come from? It comes from the probe. Likewise, if I put the qubit in this excited state, if it's qubit Hamiltonian, we make a measurement, the energy will decrease, and so the energy has to go somewhere, it goes into the probe. And that's precisely what we're seeing here in these frequency shifts. Yeah.
What are you plotting here?
So this is a color plot of the qubit spectrum as a function of frequency. So if I make a cut here, what this shows is the Fourier transform. So the question is, what do I plot? It's the power of the Fourier transform I showed you on the previous slide. And so in one case here, I see a peak like that. And so there's just a line cut. And so you can see those peaks occurring at different frequencies as they increase the frequency. And the fact that this follows this dashed line indicates that really everything makes sense in this limit, that the frequency shift we see on the probe corresponds to the qubit energy that I started, or the change in the qubit energy.
What is the central peak?
So the central peak is this is the frequency at which I'm driving the cavity. So this is omega c. And what you see is as we go to higher Rabi frequencies, I see more and more power at that center frequency. I had a speculative slide about why this might be the case. But I think I omitted it from the top. We could talk about that maybe in a little bit, why that happens. I have a couple ideas of why it is that when above a certain Rabi frequency, we start to see photons pass through that aren't shifted in frequency. But let's hold off on that for a moment. Okay. I regret having written on that, but okay. The data that we see is well matched by simulations that Shai performed of the system, taking into account sort of all the details of the setup, that we have fairly good agreement between experiment and modeling the system. And I guess you can also see that there's some nice, some interesting sort of high fine features here, which we haven't really had time to think about what causes those, but I think we may end up with a nice explanation for all these fine features that we don't solve very well. Okay. So now let's consider what happens when we increase the measurement strength of the system. So if I go back to the previous slide, we mentioned that we here the total, see, I don't think I wrote it down. Okay, the total emitted photon number is 0.2. So the number of photons that passes through the cavity in a given experiment is 0.2 of a photon. So we're in a very weak measurement regime where we probe the system with less than 1 photon on average. But now I can increase the number of photons from 0.2 to 0.9 to 3.4 to make measurements that are effectively stronger on the qubit. Okay. So I'm just showing you the data for preparing the initial state X minus, and so this is what we saw on the previous slide. We see this frequency shift. But now as we measure with larger numbers of photons, we start to see a couple different things taking place. So one, we see frequency lobes on both frequencies here is actually what we expect. And maybe that's worth mentioning. Now, I think in Nicolo's talk, we saw that the spectrum, as we measure with more than 1 photon, has had some shape like this. And this corresponds to the first photon, say, gets a frequency shift one direction, the second photon gets a frequency shift the other direction, and vice versa. And so as you go to larger numbers of photons, you start to see symmetric frequency shifts, but one of those lobes will always be taller than the other. I highlight that. What I show you here is just the spectra when the qubit is in the minus state, minus spectra, and the qubit is in the plus state, actually. Negative of that. And so we see, there's larger power in the lower frequency and higher frequency. And that persists even at higher photon numbers. So even though we see, two lobes here, one of those is certainly higher than the other. Okay, but I promised you some discussion on the quantum Zeno effect. So as we increase the measurement strength, we'll start to see the physics of the Zeno effect. So let me devote a whole slide to talk about that. So there's a lot of things going on here. And maybe the first thing to tackle is the first thing I mentioned here, that is the physics of the measurement. Okay. So there's a region down here where there's no frequency shift. We just see power at this input frequency here. And this is a region where the measurement is so strong that it's basically freezing the dynamics of the qubit. The qubit is not unable to actually, I'm not quite sure how to describe that, but there's sort of no frequency shift observed. This is also in Nico's talk, what was considered a good measurement regime. The bandwidth of the pulse is so large compared to the energy of the qubit that effectively we can make an ideal measurement of the qubit, and so we don't see a frequency shift. That's the point. And then there's a transition here to a regime where we have we do see this frequency shift. So this means there's some sort of dynamics going on in things. So, but the response frequency is less than the qubit energy here. So this is some of the physics of a damped harmonic oscillator in some sense, or similarly the PT symmetry unbroken regime. That is, even though we're driving the system at a certain energy scale, its response is slower because there's some damping. And I think we can connect this all to the physics of the PT symmetry breaking transition, or sort of exceptional points, and however you want to formulate that, there's some transition between these two regimes of frozen dynamics, overdamped dynamics to oscillatory dynamics, and there's some sort of exceptional point. The spectrum of the system will carry this structure of exceptional point.
The two lobes that start appearing in this intermediate regime, they are of the same intensity.
So I think, no, these are of slightly different intensity. This intensity is higher than this one here.
Slightly different. So
Because I prepared the system in the X minus state.
okay. So they still
but
distinguishable. The two. Okay.
So I think in the many years that I've discussed the Zeno effect, one of the formulations of the Zeno effect in my mind is that there's sort of a slowing down of dynamics, that the frequency response is broadened and shifted to lower frequency, and then all of a sudden there's no frequency response to the system that corresponds to the regime of measurement.
When you're increasing the photon number, do you see transition to higher levels, or is it not?
We haven't seen issues with transition to higher levels. I think even though our photon number is 3.4, that's the total number of photons that have passed the cavity. And so the average intercavity photon number at a given time is still quite small, maybe less than 1. And so for experts in the audience of circuit QED, there's something called a critical photon number that when you exceed that number of photons in the cavity, your rotating wave approximation that allows you to simplify the Hamiltonian to dispersive interaction becomes invalid. And we're still very far from that range of things. So this is still a very weak drive in the scheme of things. Cool. Okay. So we see this effect of the large bandwidth pulse limit of approaching a case where we can make a good measurement of the qubit because there's a large amount of imprecision or fluctuations to our probe frequency level. So that seems satisfying. Okay, so I think this also embodies the physics of the Mollow triplet. And so here's an attempt to explain that. What I'm showing here is the eigenstates of the system that combines both the qubit eigenstate and the number of photons in my probe pulse. So when we have to combine these two quantum systems together, we have this sort of hierarchy of levels that we have the qubit states split by the qubit energy. And we can scatter photons through this system, and there's different scattering interactions. So one is where just the number of photons in the cavity, for example, or the probe beam changes, but the qubit state stays the same. So that would be correspond to no frequency shift on the probe photon. And then you have a scattering interaction where the qubit makes a transition from one of its eigenstates to the other eigenstates, adding that energy to the probe photon, and therefore increasing its frequency that corresponds to this higher frequency sideband. And then there's this other case here where the qubit makes a transition from its lower energy eigenstate to its higher energy eigenstates, and that subtracts energy from the sideband. So these three processes lead to this characteristic 3 peaks in the spectrum, which is referred to as the Mollow triplet. I think this is often considered in the case of just resonance fluorescence, that you're driving the qubit as its resonance frequency, but we see this also in this case where it's really dispersive interaction between the qubit and the cavity. The cavity is mediating this frequency shift rather than the direct scattering of light on the qubit. Okay, so the final thing we can consider is the thermodynamic energy balance of this system. And here's the idea. So I can prepare the qubit in its either its lower or its higher energy state of its rotating wave Hamiltonian. And after some amount of measurement, I've dephased those states or driven them to a mixed state in that basis. And therefore, I've decreased the energy of the qubit or increased the energy by some amount that's proportional to the amount of dephasing applied to the qubit in its basis. Okay, and so that measurement of the change in reduction in the coherence of the qubit in the appropriate basis tells me about its change in energy. Okay, so based on, say, tomography of the qubit or measurement of how much measurement backaction it had, allows me to determine how much the energy of the qubits changed. And so then I can compare that to the frequency shift that I see per photon times the number of photons that have passed through the cavity. Okay. So we haven't yet done this with the experiment, unfortunately. So I'll show you just our simulation results. So so what this shows, first thing here is as I increase the qubit energy, that's the Rabi frequency along this axis here, the number of photons that pass through the cavity for a given constant drive tends to increase. And why that's the case is not abundantly clear, but as I drive the qubit, it's possible that remember that the cavity spectral density is peaked at these two frequencies here that are shifted by the dispersive coupling rate from the drive. As I do that, the sidebands, the scattering of the shifted sidebands comes closer to resonance with those cavity resonances. So the cavity is sort of more transmissive as we go to higher energy. So it lets the photons scatter through the system more effectively. And so the system becomes more transparent. And so for a given drive, we have higher photon number. So the photon number increases with the Rabi frequency. And okay, so then here I'm showing now the total energy shift comparing. So here's the energy shift of the photon. So every photon we have times the frequency of that shift that it sees. And here's the energy change in the qubit based on the qubit coherence. And so for this specific case, this corresponds to sort of a higher photon number limit. We see pretty good agreement between those two changes in energy. So this accounts for this confirms our sense of energy balance, that the change in energy of the qubit corresponds to the frequency shift on all the photons. Okay, good. So this concludes what's really the sort of first part of this talk, that the point is that when the measurement doesn't commute with the Hamiltonian, there's an energetic consequence, and the system's energy can change, and the energy change is accounted for by a frequency shift on the probe, and we're able to see this in the experiment, that in the end energy is conserved. There's some interplay between the dynamics and dissipation, which is the essence of the Zeno effect, and so forth and so on. So I have another half of the talk to describe some of our other measurements we made as part of the project, but if there's questions, discussion about this result, maybe now is a good time to take those questions.
So would you say that you've now seen the Mollow triplet in dispersive measurements and not spontaneous emission?
I think so, yeah. And I don't know if that's special or not.
I think it's very special.
I have to look through the literature to see if that's a
We call it the Cater triplet.
if that's novel or not, but that's.
So can you come back to the slide where you, so first you showed what happens when you do a very weak measurement with less than one photon and you perfectly see the shift.
Yeah.
Okay, which is consistent also what we said yesterday,
Yeah.
you know, because like you are not doing good, so you see the effect on the probe. So this is by theorem. And then when you add more photons, here I'm just so here, yeah, what I would so here you start seeing two lobes, so this sort of triplet that also we yeah, that Nicola also showed yesterday, but I would expect it to be more and more symmetric the more photons you put, because I mean, because
Yeah.
I'm trying to, of course, fitting with the theory, let's say that we presented yesterday. So the idea is the more the measurement is good, the more the thing should become symmetric, and so the frequency shift should become invisible. Is it what happens here, or maybe
So it looks, I mean, they look relatively symmetric, but when I look at the
yeah.
subtracted data here, you might expect that the contrast between the two different states decreases at higher photon numbers. And we don't, I mean, it seems like the contrast is about the same, but you may not have the experimental resolution to really say with confidence whether or not the sort of the balance of these two sidebands approaches.
No, okay.
They look like they're becoming more balanced, that we could be more quantitative.
Just yeah, just would be amazing if it would, because it would be like everything would be consistent, but maybe it's just simply because the experiment is more complicated than the model, and there is something. But do you don't have any other? You didn't go farther than 3.4 though, because maybe you are not in the good regime anymore. If you put a bit.
I'm not sure. So this is the data that Shai was taken last week.
Okay.
And so maybe he would take it also to higher dimension things. But when we go to really strong measurements, then a lot of interesting, complicated stuff.
Yeah,
comes on
of
that we
course.
may not want to have
Want
the
to
task
do
of
that.
explaining.
I see, just to have more, like if we have instead of 1%, just even some, just to see these effects that they become more balanced. Something that we can see otherwise. Yeah.
In the plot, which are in the second row, right? The colors are the difference with respect to the average.
So it's the difference. It's, you know, the power spectrum
Yes.
for the state x minus the power spectrum for the state x plus. So the difference between those two. So I record basically this graph for the two cases, and I can subtract them.
For energy concentration, I think that when you add the triple-peak structure, so starting from n equal 1.9, this difference should be more or less the same every time, even if in the upper row you get something that,
Because it's one photon's difference, effectively.
yeah, it's the,
Even as their relative heights are
yes,
relative to their, basically the same, the difference will be fixed.
yes, and
I
that
agree.
seems to be
That's the case.
confirmed.
Perfect. So if I plot the heights of these, then we'll see that they're approaching one another, they'll always be different by effectively
Yeah.
one. That's confirmed.
It's the increase, okay,
Yeah.
because you put more photons, but the difference between the two cases is always the same, because in the end, you are always changing the cubic energy by the same amount. So in the top row, you see that the spectrum increases because you go from a scale that goes from 0 to 4 to 4, and in the n equal 3.4, you go to 0 to 8. So the scale increases. But in the lower row, you see that the last two plots, they are on the same scale.
Okay.
And this seems
So
clear.
we do exactly, yeah.
Yeah.
So, yeah, to maybe to try to make it with drawings. In this plot here, we have a slightly higher peak for the, on the negative detuning case than on positive detuning case. In this plot here, if I draw it in purple, everything is twice as high. Yet there's still the same difference in the two heights. And so the two heights are approaching, the ratio of the two is approaching one. You know, one's always taller than the other. So I think the difference is the same thing. Yes.
I'm gonna admit some ignorance here. Can you go back to like one of the earliest slides, just where you're setting up in space where you're measuring in a, an observable that does not emit energy.
Like, it's sort of been.
Yeah.
Let me try to-
Yeah. So. I mean, every time I see G, I immediately think, I almoys assume it's an eigenvalue of sigma G. So where is the?
So the cubic axis is still oriented, here's Z, the Z direction. And so this is like X, and I'm not quite sure what how Shah you defined the things. This would be the X plus state, the lower energy eigenstate of that. So you can put, G in quotes. Because now in the Z sigma X basis, that's the lower energy state.
Right. But now it seems like if the Hamiltonian is sigma X, it seems like like it really does have a well-defined energy now. It's X P.
Yeah, so it has
And then it looks like these two states, the red and the blue one, have I don't know, kind of the same uncertain energy. No.
yeah, so let's see, if I just rotate our heads 90 degrees, here's X plus is now in the lower energy, down in the block curve, maybe that's intuitive there. And then so the two measured outcomes correspond to things that are C plus and D minus, and those are both higher energy in the cubic. So just find it's because our measurement interaction is fixed in the Z basis, because that's easy to do. We just rotate the energy basis.
And the initial state of the qubit is what is the current state of sigma X?
Yeah, so the initial state of the qubit, I'm showing you later things, the ground state of the Hamiltonian. So that's the state here. That's different than what Niccolò was showing, where he was preparing the qubit in the ground state of the Z operator. So there's some dynamics taking place while the measurement takes place. But here, really, we're preparing it in the eigenstate of its Hamiltonian, not the measurement Hamiltonian.
And so it gains like 1/2 quantum in this.
Yeah, half of the qubit energy, which is what we call omega. Since the total energy gap is 2 omega.
Suppose that the initial state is some unknown pure state. And is it possible to measure it and kind of reconstruct the possible selections of the initial state just by observing the frequency shift?
So let's see if I can understand your question correctly. So the system is in an unknown initial state,
Unknown pure initial state.
an unknown pure initial state. So it's in maybe the X plus X minus some state, and we just measure the frequency shift that we observe. Can we use
Yeah.
that to back out what the initial state was?
Yeah.
Because a little similar to what Niccolò is saying is it possible to sort of figure out how does the measurement record tell us about the initial state? And so I think in principle, that's possible to back out what the initial state is.
So I think that when you try to do the measurement by looking at the spectrum, what you can measure is the state of the qubit in the energy basis. Because the two spectrum will be different based on which was the spectrum of the, which was the state of the qubit in the energy basis. And therefore, like, for example, if you send just one photon, okay, and you have the ideal thing in which you have a blue shift or a red shift, you measure the spectrum, and then you can infer what was the state of the qubit in the energy basis, not in the Z direction.
What did you think?
I
Oh,
think
okay, yeah.
that was the question.
Oh, good.
So it's not clear to me, off the top of my head, whether or not, just looking at the spectrum is, we're losing some information about the system. But I know that if I take the full measurement record system, I can use that to, if I know the initial state, I can track individual quantum trajectories of the system, know what the final state is. With high certainty. And so I can also run that in reverse. If I have some final state of the system, I can take the measurement records and reconstruct those backwards to guess what the initial state was. So I think that one can determine what the initial state was based on the measurement record. Quite well.
But another more interesting case is I'm concerned with, how about the mixed state? Like, suppose we have a ferrite state and we measure locally one of the qubit, so which would be a kind of improper mixed state. And how would the spectrum like be like in that case? And when we reconstruct the possible, so suppose we assume that the improper mixture state is a pure state, which may or may not be true. And if we try to reconstruct the pure state by observing the energy shift, like how would it be like?
So yeah, so if we start off in some perfectly mixed state, and now we have a measurement record, we try to back up what was the initial mixed state that we had. Maybe the resolution is the mixed state is a mixture of two different pure states, and so we can use the measurement record to like uncover the unknown initial pure state that it was in. But I think when we start thinking about racking measurement records back in time to ask about what things were in the past, we have run into very interesting parts of quantum mechanics, and, post-selection, but I think that there's so there's plenty of room to determine what the state was in the past and find interesting conclusions.
On the other hand, the single qubit measurement can't tell you if you're initially entangled or it's thermal. There's no way you can do as a local measurement to determine that. It's
Yeah.
So I was, so just, so can you explain again why are you calling this regime of perfect measurement where you really don't see any spectral deformation? You are calling it Zeno regime because it's like implying that the measurement happens so fast with respect to the internal dynamics that there is no time to accumulate the shift. This is the idea. But because I since some website on the idea like all is simply just when the measurement is good, you don't see. I never thought in terms of Zeno effects, in terms of time scale somehow. But actually rephrasing it in terms of Zeno effect means say adding this, not adding like it happens fast.
Yeah,
the idea.
The measurement is so strong that there's no time for the system to
Okay,
evolve.
yeah.
But I think more importantly is in the absence of measurement, the system can undergo some evolution, but the measurement prevents that evolution.
Prevents that, yeah, because
Normally, we think about the Zeno effect in the context of closer to it. If I prepare the qubit in the not an eigenstate of its Hamiltonian, so it's undergo some unitary evolution, but the measurement pins it to that initial state.
now it's the opposite.
And now we're putting the qubit in a stationary state of some Hamiltonian, but the measurement is affecting. But I think it's the same parameter regime that corresponds to Zeno effect. So maybe it's a static case of this.
No, but it's fascinating. This is kind of this theorem that Nico was saying yesterday. This idea is also for any kind of measurement where you have the something, and then when you are analyzing this specific system where the dispersion of the quantum meter corresponds to the time, it becomes the Zeno effect somehow, that it becomes the physical reason why you don't see the shift. I don't know, maybe I'm like, but you see my point, because the general term says, if you have a meter that has a broad dispersion, you won't see the effect of the measurement on the meter, so you won't see the energy shift. This is a general term for any kind of meter. Then when this dispersion is on time and frequency, it becomes a fast measurement. And so it's also the explanation, as you say, the straightforward is zero.
So, yeah, I think so.
Something like this, because in the end you explain it in this way, but it's, yeah.
I mean, I think in that way, the Zeno effect is just a competition between the Danvik
Yeah.
and the unitary evolution.
Yeah.
And that's just fine. Okay, perfect. I think that's probably a good place to stop there. I could have talked another little while longer on our measurements where we're using, trying to make measurements of a qubit using actually the same setup, using thermal light and asking a question about, can one make measurements with purely thermal resources? What's the price one pays for using thermal resources to make those measurements? And this was a really surprising experiment because we found that, in fact, there was no disadvantage to using just good old-fashioned thermal light. The noise from a room temperature resistor to make a measurement of the qubit compared to very fancy coherent states generator with an expensive vector signal generator. And a result that is so surprising to our colleagues that we're still sort of sorting out why it's the case is corresponding with Benjamin O'Watt's group, that there should be some price to thermal resources, but in this case of strong dispersive machine, we're able to see qubit measurement just with thermal resources. That was, I think it's a victory for experiment because the experiment gives us constant confidence that that's what's going on, even though theoretically it's quite surprising.
But you pay at the erasure.
But we pay at the erasure. So in the end, when you think about the full quantum, full thermodynamic cycle of the system, there is an expense to the resources that it generates more entropy in the cavity than information generated about the qubit. So there is a disadvantage in that fundamental case. And the only real advantage is actually using single photons to measure the state of the qubit. So that's all summarized in a PRL that we all wrote. So if you want to read about that, you can. But I think I will stop here. So thanks for your attention.